Solar panels, wind turbines, hydropower, thermal power. We are developing and improving technologies to get rid of non-sustainable energies such as coal or oil. But there is still one little known yet powerful option: osmosis, also known as blue energy. What is osmosis? Let's say that you have two liquids, each with different concentrations of salts, separated by a membrane. Osmosis is the exchange across the membrane that allows the concentrations to become equal. Osmosis can work by letting water through the membrane. Osmosis also works by letting salt ions through the membrane, which is why it has the potential to create electrical current. This is the phenomenon that EPFL researchers are taking advantage of with their new prototype, which was the subject of an article in the journal Nature. They developed a small device with two liquid-filled compartments separated by a membrane. The membrane has a tiny hole, also known as a nanopore. In the first compartment, the liquid has a high concentration of ions. The ions cross the membrane to establish equilibrium with the second compartment. For each net ion that passes, an electron is transferred through an electrode, generating an electrical current. But the real novelty here is the membrane. Indeed, the membrane is incredibly thin, barely 3 atoms thick. And for this technology, the thinner the membrane, the more current generated. The nanopore is negatively charged, which means that it normally repels negatively charged ions while letting positive ones through. Given this selectivity, one compartment tends to be positively charged and the other compartment tends to be negatively charged, somewhat like the poles of a battery. This is the main reason why the voltage increases. So to summarize, the thinner membrane equals more current, and the selective pores equal higher voltage. As we all learned from Electricity 101 and quite possibly forgot, power equals current times voltage. It's the famous P equals I times V. If we reduce the size of the nanopore, the voltage increases, but there is less current. If on the other hand we increase the size of the nanopore, the current increases but the voltage decreases because the nanopore is less efficient at selecting positive ions. By playing with the diameter of the nanopore, the researchers were able to find the ideal compromise between current and voltage to obtain the highest possible power. In order to understand exactly what happens, the researchers built a basic prototype with only one nanopore. The electricity generated was enough to power a molybdenite transistor. But that same surface could potentially harbor billions of nanopores. To top it off, the materials are readily available and cheap, which means that once we work out how to manufacture its pores uniformly, the ultra-thin membrane can be produced on an industrial scale. Theoretically, the maximum yield of the device is impressive. For a membrane that is 1 square meter and with only 30% of its surface covered with nanopores, we could reach 1 megawatt. Enough to run 50,000 standard energy-saving light bulbs. This is a very promising source of renewable energy. Solar panels only work when the sun shines, and wind turbines when the wind blows. But osmosis can be used in river estuaries, where fresh water meets seawater, and could potentially work all the time.